Y'all ready for this? Chapter 11, capacitance. Capacitance. If you believed what I sold you last chapter, this should not be a stretch for you. Because it's kind of like the same thing is happening, but with a different property. It's really what it's all about. But capacitance is actually kind of cool. We'll talk about it. A lot of uses for capacitance. After completing this chapter, the student, you, the student, will be able to explain the principles of capacitance, identify the basic units of capacitance, identify different types of capacitors, determine total capacitance in series and parallel circuits, explain RC time constants, and how they relate to capacitance. Capacitance is the ability of a device to store electrical energy. Let me stop. The ability of a device to store electrical energy. What does that sound like the definition of? Mr. Carter. That sounds like the definition of a battery, doesn't it? The ability to store electrical energy. So there's really not that big of a difference between a capacitor and a storage cell. Typically a storage cell is a small amount of current over a long period of time, unless you're a car battery. But a capacitor generally is a large amount of current over a short period of time that it's designed to expend, if you will. But the definitions are very, very, very similar, very close. The key word on how a capacitor works is that electrostatic field. Electrostatic field. Remember inductors, they were electromagnetic. This is electrostatic. Electrostatic. Talk about that property a little bit more in a bit. The letter C stands for capacitance. So inside a schematic diagram, if you see a letter C equals, it's capacitor. If you see C22, it's capacitor number 22 in the circuit. C47, capacitor number 47. A capacitor is a device that possesses a specific amount of capacitance. How these things are made are two conductors separated by an insulator. Two conductors separated by an insulator. What does that sound like the definition for? Close your eyes and think about it. Two conductors separated by an insulator. What does that sound like? Battery. You made that up, man. And what would the definition of an extension cord be? Two conductors separated by an insulator. What would speaker wire be? Yeah, so you know what? There are going to be a lot of things that have capacitive properties because they're two electrical conductors separated by an insulator. And a lot of these things that have capacitance is stray capacitance and capacitance that we don't necessarily want. Engineers don't want, but we have to deal with it because it's two conductors separated by an insulator. Anytime you do that, you're going to end up with the property of capacitance. Anytime you coil up your welding wire, your welding leads, electro leads, you're going to create some inductive properties.
The old flat TV antenna wire from the 1950s.
Yep. Yep. And that actually, believe it or not, that style of twin lead antenna cable, it was some of the most efficient. When properly installed, it had higher efficiency than coaxial cable. The only thing is people would get that nice ribbon cable, and then back in the day, right, growing up in Connecticut, you know, we had aluminum windows, and you'd route it through the window and then slam the window down on it, and there goes any advantage that you had. But when you use the proper standoffs and you know, you use the proper bend radius and everything else directly to the back of the set that had higher efficiency, it would get more RF energy into the back of that television set than using coaxial cable. But it was two conductors separated by a thick dielectric, thick insulator material. So that's one of the things I really want you to come out of these lectures with, is understanding that, you know, this is not a lecture about capacitors. This is a discussion about capacitance and capacitors. But the biggest thing is, when you get into some of the advanced classes, like Peter Welty and his PCB design class, it's one of the biggest challenges is determining stray capacitance inside a circuit. When we're physically trying to create capacitance, we're going to call the conductors plates. And we're going to call the insulator dielectric. So two plates separated by a dielectric. Now that, Mr. Carter, is the definition of a capacitor. Schematic diagram up at the top is a fixed capacitor, meaning what you see is what you get. Within tolerances, of course. Down below is a variable capacitor. There's actually different ways that they're going to be able to vary the capacitance. One is going to be varying the distance between the plates. We'll talk about this more in a bit. And the other is meshing the plates, where they don't physically touch, but they're just closer proximity. More in closer proximity to each other, less in less proximity to each other. Make sense? Treat all capacitors as though they were charged. Never touch both leads of a capacitor with your hands. I've got a capacitor. Where the heck it went? I got to get my stash better organized. Stuff disappears in here. Actually, I had a student that worked for one of the biomedical companies, Medtronic, and they had the starter jumper kits for when you die. It's great. I see them. They got like Costco, you know. You just got $680 worth of stuff in your cart at Costco. You drive your car and they revive you on the spot. Make sure you pay your bill. Airlines got them now. We're going to charge you $25 for that bag to check it. You know, you have a heart attack, they revive you. You know, just let me die here. Anyway, had a student at work there, evening student of mine, and he brought me a capacitor that was a key component in that. And right on the capacitor was a label. The energy stored in this device could be lethal. The energy stored in this device could be lethal. So if that capacitor is charged up and I toss it to you and you touch it, it'll kill you dead. Because you're building up all of that charge and then rapidly discharging it through your body, which it's not designed to do. Capacitor can hold that charge potential indefinitely if it doesn't have a discharge path. A theoretically perfect capacitor will hold the charge forever. Because of manufacturing flaws and defects and stuff, eventually that current will dissipate. I remember when they were, I've been here for a while, not when they were building this building, not when they were building that building, the new one, not when they were building this building, but when they were building that building, like 20 years ago. And there's actually a time capsule buried out there somewhere. And they were looking for ideas from, you know, I'm like, let's charge up a capacitor and put it in the time capsule. I mean, as an electronics guy, I think that'd be cool. Like, great, let's take it out of its protective covering and see if any voltage is still present. I mean, I would have gotten a kick out of it. They're all looking at me like I'm a goofball. You know, I mean, don't you think that would have been an outstanding freaking idea?
Will a battery hold indefinite charge as well too, or will that dissipate faster?
Because of the chemicals, a chemical cell will eventually dissipate. So it has a shelf life. Lithium batteries have the longest shelf life. I mean, those, what are they? The Energizer or whatever that you could buy, lithium, best batteries that you could buy. Very great product, innovative product. If you absolutely positively have to have a portable electronic device work, operate under extreme temperature conditions, whatever, great shelf life, use those batteries. So I just bought some, and I think that it's good to the year 2025 or something on it. It's like, wow, that's a shelf life. The basic unit of capacitance is the farad. A farad is the amount of capacitance that can store 1 coulomb. Remember the coulomb? 6.24 times 10 to the 18th electrons of charge when a capacitor is charged to 1 volt. So we got a couple different things going on there. You got these 2 plates, and what you're doing is you're charging it, and what it's doing is you're physically loading those plates up with a large number of electrons. And then you're building up an electrostatic field across those 2 plates. So when you build up 1 coulomb across the plates, we're able to store 1 coulomb of charge and bring the capacitor up to 1 volt. We call that a farad. Now, typically the values that we're going to work with in electronics are going to be centered around the microfarad. The typical value of measurement of capacitance is the microfarad, which is times 10 to the negative 6th. And also the picofarad, which is times 10 to the negative 12th. So we go from the 6th to the 12th. What's between 6 and 12?
The
Nano. You know, for the longest time I used to put out in lecture, you will never see a nanofarad capacitor, because they didn't used to make nanofarad. Actually, you know what they used to call nanofarad capacitors? Millimicro. Millimicro, 3 places past milli. No, micro. Millimicro. 3 places past micro, which would be nano, so we call that, they'd call it millimicrofarad, MMF, millimicrofarad. Or they would call it tens of thousands of picofarad.
Why'd they refuse to use nano?
I don't know if it was a small letter N that just like freaked them out. Seriously. I mean, sometimes it boils down to that. It was, you know, they'd have this Congress that would meet and analyze the stuff, and they just wouldn't. So I used to put it out in lecture. You will never see a nanofarad capacitor. Whenever I put out absolutes, somebody feels compelled to prove Joe Grenick wrong. So the next day, student, hey, you know, I found this, my company's using these, what's this? I, you know, showed it to me. It was like a 20 nanofarad capacitor. Great, you're doing it. It should be a 20,000 picofarad capacitor, or a 20 millimicrofarad capacitor. But, and that's, I'm intentionally talking to you about this because traditionally, capacitor values have been all over the place as far as how they label them and how they identify them, and sometimes determining what size capacitor is very, very difficult. And what a manufacturer labels it as. I mean, resistors were easy with color code. Sometimes you got to trust the packaging on these things. What's up?
Do you remember what the farad rating of the capacitor that the guy brought in from the defibrillator was?
No.
High?
Yeah. Yeah, I mean, enough to kill you. But yeah, you could really, and don't do the stuff here. I mean, that's one of the things. Again, we take safety seriously, but some of those big capacitors, charge that up, leave that there, or, you know. In the Navy, which was different, we were government property, you know. We always used to do that crap, you know, charge it up. It's like, hey, check this out, you know, here, catch. Pshaw, you know. Stuff freaking hurt, man. It wasn't funny. Go up to somebody with a charged capacitor, man, stick it on their neck. Cha! Yep, these people were entrusted with our nuclear arsenal. Basically, that's a high discharge device. You're using capacitors and inductors in there to create a high voltage to make someone compliant. A capacitor is either fixed or variable. A fixed capacitor has a definite value that cannot be changed. It's made a certain way, if you will. A variable capacitor is one whose capacitance can be changed by varying the space between the plates or by varying the amount of meshing between two sets of plates. Although they say mesh, the plates never touch. They have to be kept electrically isolated with an insulator in between, and that insulator could be air. Factors affecting capacitance. Now this is kind of important to understand these. If you understand these, the math makes a lot of sense. The area of the plates, right? The bigger the area, well, actually, let me put that formula up on the board, right? C is equal to Q over V. Remember that? Capacitance measured in farads is equal to coulomb brought to a volt. 1 coulomb brought to 1 volt equals 1 farad. Make sense? So area of the plate, what effect is that going to have? Is that going to affect Q or is that going to affect V? Q. The bigger the plate, the more electrons I could park on the plate physically, right? Because even though electrons are electrons, they still take up space. They still are comprised of matter. So very good. So the bigger the plates, what effect is that going to have on capacitance? Bigger plate, more capacitance. Smaller plate, smaller capacitance, right? Because Q and C are directly proportional, right? Because Q is sitting up on top of this here. Distance between the plates. Distance between the plates, what's that going to affect?
Static field.
So what's that going to affect? Q or V? Think of the distance between the plates as like regapping a spark plug. That's the distance between the electrodes. This is the distance between the plates. The further that you move those plates away from each other, the higher the voltage you could store on those plates. And that's where engineers have to determine, what am I trying to do here? Am I trying to store a lot of electrons? Am I trying to have a high voltage that I'm trying to build up across it? What am I trying to do? So engineers have to take that into account. So if I separate the two plates, that means my voltage that I could store will go up. If my voltage goes up, what's my capacitance going to do? It's going to drop. So engineers are faced with this compromise. Higher voltage I could store, but I'm going to get less capacitance out of it. Why is capacitance going to go down too? Well, when I separate those plates, that electrostatic field is going to diminish because the plates are physically further away from each other. So you separate the plates, get a higher voltage on it, higher voltage, lower the capacitance. The type of dielectric material, what effect is that going to have? What's that going to affect? The type of dielectric material. Is that going to affect the Q or the V? Or the C? Well, I think it's going to affect the C, yeah. Why? Because of Q or V? Think about this one. What's it going to affect? Q, bzz.
Wouldn't it affect both?
Bzz. It's going to affect the voltage. Because if I've got two plates separated by air, and then now instead of the air I slip in a piece of mica, mica has a higher dielectric constant than air, does it not? Remember you guys are deceiving me, man. Remember those lectures early in the quarter? We talked about different types of insulators. Mica was at the top of the chart. So if I slip a piece of mica between those two plates now, I could actually have those plates real close to each other and slip some mica in there and really get a high voltage across those plates. Get a higher voltage for the distance because I'm using a dielectric material that has better dielectric properties. So that's how that's going to affect V. Affect V, it's going to affect C. And then temperature. Temperature. How is temperature going to affect this? What changes with temperature?
Resistance.
Yeah, but we're not talking about resistance here, so. It's actually simpler than that. It's something probably that you all knew even before you walked in here. Things expand and contract with temperature. Right? That's why there's expansion joints on bridges. Right? Because bridges expand and contract, and if not, they'd break. You know, oh no, it got over 70 degrees today, the bridge broke. You know, no, expansion joints, because things expand and contract. Capacitors are going to expand and contract. So as the plates expand, it can hold or affect Q. As the distance between the two changes, it's going to affect V. So the bottom line is the amount of capacitance will vary with temperature. For some circuits, like at room temperature, it's not that big of a deal. For some stuff, I don't think in your wildest hallucinations you've ever really thought it through where a lot of electronic systems are used. I mean, it's a pretty harsh environment. My favorite aircraft of all time, military aircraft of all time, I just get so jazzed when I see one, is the F-15 Fighting Falcon. Okay? These things were designed as high-altitude interceptors. The closest to us right here are Portland, Oregon, the Oregon Air National Guard. So if you've ever flown commercially in and out of Portland or been down there, you might be on an Alaska Airlines jet that has to give way to two F-15s that are taking off in front of you. The F-15 still holds the unclassified time to climb record, 45,000 feet in 1 minute. That basically means you're sitting at the end of the runway at Portland International Airport. They give you the thumbs up, clear for takeoff. You advance the throttles, you kick in the afterburner, and next thing, 1 minute later, 60 seconds later, you're passing through 45,000 feet. These things are so good, they used them last summer when President Obama was in town. And there was a small plane that penetrated the airspace up here. Guy was flying into Kenmore in a float plane. And they're watching them on radar, and they got concerned. So they called up the Oregon Air National Guard, and they said, we know you got a couple fighters there and ready standby. I think it's time to scramble them. And these guys are like, woohoo! Because what they did is they not only got to take off, but they got to go supersonic. They got to go on an intercept call. So what they did is they went supersonic. I'm sure you all heard about it with the windows getting knocked out and the sonic booms. Okay? Where I'm going with this, though, is imagine that airplane sitting on the runway down there in the middle of summer, sitting on the tarmac, 115, 120 degrees, and then 60 seconds later, he's at 45,000 feet where it's negative 45. If electronics are not all in heated areas of that aircraft, so if you've got a capacitor that is in an area that is prone to temperature change, you're going to get different results. Hopefully that's not part of a targeting system on that aircraft where all of a sudden, you know, and the military's smarter than that. The reason temperature that it always strikes a chord with me, I was not always the best student, especially when I was in a lot of military schools. I went through over 4,500 hours of military schools, different systems. I was in a great position because as soon as the Russians came up with something, we had to come up with something to detect it and counter it, and I was constantly in school. Traveled through 46 of the 50 states on official business going to school, a lot of factory schools, a lot of stuff. Long schools, and it was not a school day like yours. These are 8-hour days. 8-hour days, 5 days a week. And it was back in the day, old school. So we used to go out for liquid lunches. And I mean, I used to sit in back. And I was sitting there one day, and I'm like, you know, falling asleep and hopefully not snoring too loud. And I wake up, and the instructor is showing me this, you know, they have the presentation, and they had, not PowerPoint, they had the view foils, and they're showing this oven ready light coming on. And I'm like, oven ready light. Oven ready light. I'm in electronic intercept and analysis. why is he talking about an oven-ready light coming on? I mean, if this is like, I picked the wrong time to wake up because I don't have a freaking clue what he's talking about. An oven-ready light, and I'm just trying to wrap my mind around it. And actually what happened is this equipment was so sensitive, it was very secret special equipment for measuring these very specific emissions from Soviet equipment, that they put key sensitive temperature components in what was called an oven. And what it was is a small metal box inside the piece of equipment, and it had a heating coil and it had a thermostat, and it would keep that temperature stable so that the readings would be stable. And if that oven-ready light was not on, that told the technician that the oven wasn't on, and the numbers, the results, could not be trusted. So that was a big thing before you use that equipment, is verifying that oven-ready light was on. It was like, it's funny, because even though I slept through the lecture, I still remember it like it happened yesterday. This is not an endorsement to fall asleep in class. But it was a blue light. It was this blue light. And I always remember, because I'll tell you what, we had our labs were written tests, and then we had practical labs that you had to go in and troubleshoot that equipment. And I remember that the day I went into, I was basically being evaluated. I had 2 instructors standing in there with clipboards, and, let's see how Petty Officer Grenick evaluates this problem here. So I walked in, and the first thing I noticed is the blue oven-ready light was not on. So I knew immediately where the problem was. And I told him, oven-ready light's not on. There's a problem with that circuitry. Got in there, and basically there was like a fuse that was blown, replaced the fuse, boom, fixed the problem. If you're not a vigilant technician paying attention to that, oh yeah, you could run through all the tests. Oh, everything's working okay. So some key components like capacitors that are in real critical roles in circuits may be put in a circuit or in a box called an oven where they keep that temperature really stable. For most stuff like this, inside buildings and, whatever, industrial controls, it's normally not an issue. Normally even an automotive application, I've never heard about anybody, and actually cars are pretty freaking robust when you think about it. I mean, I've been down in Arizona in the summer, it's like stuff is melting, plastic is melting, your tires are melting on the cars, it's just nuts, And I went up to Alaska here in February, and that was like the week before I was up there, it was -47. So you go to Fairbanks Airport, you land, you're going to rent a car, and it's buried in snow, but you just follow the extension cord from the post, and it's all on a block heater. You can dust it all off. It's all powder snow up there because it's so cold and so dry. Turn the key, fire it up. Every place you go, the hotels all have a place to plug into, though. I mean, it's just, but still, that extreme cold is like, wow, the electronics work reasonably well from Arizona to Alaska. Keep these 4 factors in mind. They're critical. Dielectric constant, this is the measure of the effectiveness of a material as an insulator. Some materials of dielectric constants, paper has a dielectric constant between 2 and 3. Typically what they're talking about here is wax paper. Wax paper. Wax paper used to be used as the dielectric, as the insulator in a lot of capacitors prior to World War II. I've actually restored many an antique radio by simply going in, removing the paper caps that have deteriorated, and putting in mica caps of the same value. Just that easy, remove it. Everybody always gets an old radio, and oh yeah, it must be them there tubes. Them tubes there need to be replaced. I've restored a handful of radios, haven't replaced 1 tube. Got in there, replaced the capacitors. Why? Paper capacitors. What happens to paper over time? Deteriorates. It deteriorates, loses its dielectric constant, capacitor shorts out, doesn't work. Mica, dielectric constant between 5 and 6. This should be tantalum, not titanium. Titanium, they're using that in golf clubs, in Soviet submarines. This is tantalum. Tantalum is a material that has a high dielectric property. So by putting it in a tantalum capacitor, it gives you a big bang for the buck. Some of the best capacitors that money will buy. Tantalum. Electrolytic capacitors. These are large capacitance for size and weight. Consist of two metal foils separated by fine gauze saturated with a chemical paste called an electrolyte. They're polarized, having a positive and negative lead. If you put an electrolytic capacitor into a circuit backwards, it will explode. Literally. If you put one of these in a circuit backwards, it will explode. Some of the smaller caps actually have where, like, there's an X etched on the top, so when it blows, it'll blow outward and not necessarily build. I don't know. I knew a guy that likes to play around with explosives and stuff in the past. You know, and it's all about keeping it compressed, those gases, you know, compressed, and it's going to give you a bigger bang. So some of those small caps that don't have a little release mechanism on that, you can throw some shrapnel. Some of the big caps actually have a release valve on it, so if you put it in backwards, pow. But I've seen smoke pouring out of them like a smoke bomb. If you ever want to blow up caps, let Peter or myself know, and we want to do it in a controlled, contained environment. You just do it for kicks in the lab. Somebody could lose an eye, seriously. You know, because they're little metal cans, and you put it in backwards, these things blow, shrapnel is going to go flying.
You guys actually have a controlled area that you can do that?
I've done it before out in the back. You know, we rope off an area, and it was actually funny. We were doing that, it was one evening years ago, blowing up capacitors, you know, and pow, 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 pow. We're putting them in series and parallel and doing all kinds of wacky stuff, you know. And literally, we were doing it in the back here, and you know the second floor up above the restaurant, that patio area between the two buildings? I had debris raining down on that. So nobody really cared about it until I went to the custodians and I asked for like some you know, brooms and stuff to clean it up. And then it was kind of like, well, they all got puzzled and stuff because they're like all union here. And they're like, if it's a mess, you know, we need to clean it up. It's like, well, no, my students made this freaking huge mess out here for blowing up crap. Well, no, we'll clean it up, you know. And, oh, I'm sorry, you know, file a grievance because we're going to clean up the mess we made, you know. So it was just an odd time. I guess it's still an odd time, you know, here. But it's my personal collection of capacitors. These are all electrolytic capacitors. And on the electrolytic capacitors, you got to look for the markings here to find which lead is the negative lead and which one's the positive lead. And there will be some discerning mark on it. Some manufacturers identify the negative lead, some identify the positive lead. You just got to pay particular attention. This here, like with the band on it, that would signify the negative lead. See that solid band? You just got to look and be observant. Put it in backwards, it will explode. Paper and plastic caps, construction by a rolled foil technique. Plastic film is often used more often. Basically, if you went and got 2 rolls of aluminum foil and a roll of wax paper or a roll of saran wrap, right? Laid out one roll, put the insulator on top of it, laid the other roll out. We rolled it all up, dipped it in wax, attached leads to it, dip it in wax. You just made yourself a capacitor. So if you want to roll your own, you can roll your own. You make it out of paper, same thing. And that's exactly what paper caps were. 2 pieces of foil with wax paper between them, the leads attached, dipped in wax. That was it. And that wax didn't prevent that paper from deteriorating over time. These are plastic caps here. Basically, if you slice that open with an X-Acto knife, you'd find nothing but rolls of aluminum foil wrapped around plastic. Ceramic disc capacitors, popular because they're inexpensive to produce. They're used for values of 0.1 microfarad and smaller. Ceramic is the dielectric. They're reliable general purpose capacitors. This is my personal collection. I get all my ceramics from Mexico. I get a lot of them manufactured there.
How come that doesn't have any positive marking leads on it?
It's not electrolytic. Ceramic. These don't have a positive and negative lead. It's only the electrolytic that does. Check out the value of this. This will 3 kV. It'll hand up to 3,000 volts. You exceed that, you destroy the capacitor. You operate all day long underneath that. Variable capacitors are also known as padders, trimmers, or tuners. This is a tuning capacitor. This is something you'd find in a 1960s, 50s, 60s, 70s radio. Elegant. Elegant in design. I mean, they don't make stuff like this no more. I mean, how many of these went to the landfill? A lot of these, the shaft right here, this would actually be a ball bearing movement right there with a heavy grease in there, and you turn it ever so slightly. And actually what they would do with this is they put a big pulley on here, and then there'd be a string that was attached to your tuning dial. So when you move that knob just a little bit, it would ever so slightly move that tuning cap, and that's how you would adjust. By adjusting the capacitance, you would tune your radio. Now it's done all electronically. So this is something kind of from a bygone era. Which is good and bad in some ways. I don't know. Tell you, well, I don't think these new tuners have the sensitivity that those old tuners had. And I saw the transition in the military. When I first got into electronic intelligence gathering, they were manually operated tuners. I mean, I used to have to sit there and manually tune through, find a target of interest, intercept it, analyze it. I saw the transition to computer-operated systems, and it boggled my mind. I rode my submarine out here, and my sub was going to get a new system, so I rode it here. The work was being done in Bremerton, then they flew me back to Connecticut for the summer. Actually, I drove. It was kind of funny. I used to tell the Navy I had a fear of flying. That's why I'm in the Navy. So because I was going to so many schools, they'd pay me to travel. So it was like, I don't know, 300 miles a day per diem and hotels and whatever. So I used to get 14 days off to drive to Connecticut, so I'd go to San Diego and goof off for a week and a half, and crap, and I marathon across the country or whatever, you know. But anyway, I was getting sent to this school where it was going to be computer-controlled receivers. And I'm like, computer-controlled receivers? I mean, it's like some robotic arm is going to come out and tune the dial? I mean, how do you do that? I mean, I'm serious. I had no freaking clue what they were talking about. And that's not what they were talking about. But I just don't think we ever had the sensitivity that those old manual tuners had. The newer systems, of course, were much more efficient, and once you integrate computers, you can process the data. The data is only getting processed as well as it was programmed. But yeah, those old tuners, boy, I could listen to some stuff way out there. We'd be way the heck out in the middle of nowhere, and I could tune stuff in with a good antenna and good receiver. Series capacitors. Yeah, you're not looking at a typo. When you have capacitors in series, you treat them like resistors in parallel. Does anybody know why that is? Why do you suppose? It's a good try. Okay, these three capacitors are in series, are they not? What am I really limited to here? I'm limited to this plate area here, am I not? And this plate area here. What am I actually doing? I'm increasing the distance between the plates, which means my voltage goes up. That means my capacitance has to go down. Make sense? That's why that formula works. Plus, I'm getting 1, 2, 3 times the insulated material, as opposed to 1 time the insulated material. Make sense? So everything always goes back to this formula. Everything in electronics always is explained away with a formula. In parallel, what am I doing here? I've got this plate, and this plate. Now here I triple the size of my plates. I tripled the size of my electrostatic field that I could build up across the two. So what am I doing? I'm increasing my Q, which increases my C. That's why that formula works. So I don't know if that helps you, but it helps me remember formulas if I understand how the formula works. If I just give you a formula, C is equal to Q over V. Okay, I'll remember that. That's not going to do you any good. If you remember C is equal to Q over V, increase the area of the plates, I could store more Q, Q goes up, C goes up. Distance between the plates increases, V goes up, C goes down, inverse proportional relationship. Make sense? RC time constants reflects the time required for a capacitor to charge 63.2% of the applied voltage or to discharge down 63.2%. It's not a typo, it's the way I worded it intentionally on this slide. You're decreasing down 63.2% to 36.8%. This is what the circuit's going to look like. This is the formula. T is equal to R times C. It's going to take 5 time constants. And physically what's happening with this, what kind of a circuit is this? Series. Series RC circuit. It's a series RC circuit. And when I close this switch, this capacitor here is going to be at 0 volts and it's going to start charging up to 100%. How long is it going to take to get to 100%? 5 time constants. How do I figure out what 1 time constant is equal to? T is equal to R times C. When this capacitor is at 100%, what voltage is going to be across R1? Bzz. When capacitor C1 is at 100% after the passage of 5 time constants, what voltage is going to be present across R1? 0. When 63.2% of the voltage is across C1, where's the remaining voltage going to be? Across R1. So basically, as the capacitor is increasing in voltage, the resistor is decreasing in voltage. Because this is not only a series circuit, it's also a voltage divider. It's a voltage divider. After 5 time constants, this voltage will be equal to this voltage. Voltage rise, voltage drop. After 5 time constants, this is equal to this, which means there's 0 left over. Kirchhoff's voltage law. Everything always goes back to what we talked about. I'm really not talking about a whole lot of new stuff here. Getting paid to talk about the same old stuff. Just every week I introduce a new word. This week it was inductance, capacitance.
What is it 5 times?
Why?
Why not be 2?
Because in 5 times you basically get close to 100%. That's why we call it 5 times. It's really between 5 and 6 times. Some books say 6 time constants. Some say 5. But you're so close to 100%.
Because the 6 would be 63% of 99.3% then for the 6th consonant? Because on the 5th consonant it would be 99.3%, right? Right?
After 5 time constants, we call it even. We just say.
But the books that you say do sometimes have a 6th time consonant.
Well, yeah. I mean, if you're dealing with real high power stuff, that could be a difference. If it was high power and a high voltage, it could be the difference of a couple volts, that small percentage. But generally, it's accepted 5 time constants. Every exam you take here, it'll be 5 time constants. In summary, capacitance is that property that stores energy in the form of an electrostatic field. A capacitor is a specific device designed to possess the property of capacitance. Fixed capacitor symbol on the top, variable capacitor symbol on the bottom. Capacitance is measured in farads, developed by a guy by the name of Joe Farad. Microfarads, picofarads are typically the most often used values. Instead of nano, you may see milli, micro, or you may see tens of thousands of pico. The letter C represents capacitance. Four factors affect capacitance: area of the plates, distance between the plates, types of materials, and temperature. Capacitor types include electrolytic, paper, plastic, ceramic, or variable. To add up capacitance in series, you use the parallel formula. To add them up in parallel, you use the series formula. And to determine capacitive time constants, we use the formula T is equal to R times C. Any questions? All right. Let's go ahead and take about a 10-minute break. And when we come back, section 2 of the book, AC circuits.